Friends, one-dimensional wave equations. Suppose OA be the stretched string of length L with fixed ends O and A. So OA is a stretched string. It is of length L with fixed ends O and A. Let us take x-axis along OA and y-axis along OB, the perpendicular to OA with O as origin. Let us plug the string in BOA plane. So here the string is plugged in BOA plane. So BOA plane, we have to just plug the string. Suppose let P be any point on the string at any time t. Let each point of the string make small vibrations at right angles OA in the plane BOA. So in plane BOA, we have small vibrations which make the string. And we have a right angles to OA in the plane BOA. Now using the Newton's second law of motion, it can be proved that y of x comma t governed by the equation dou square y by dou x square is 1 by c square into dou square y by dou t square. Suppose let it be equation 1. So this equation is known as one-dimensional wave equation, where c square value is t by m and t is tension in the string at any point and m is the mass per unit length of the string. Since the points O and A are not disturbed from their original positions for any time t, we will have end conditions. The end conditions are y of 0t is 0 and y of lt is also 0. So y of 0t is 0 and y of lt is also 0. These two conditions are known as boundary conditions or end conditions. Further, it is possible that we describe the initial position of the string, not necessarily along the equilibrium position, as well as the initial velocity at any point of the string at a time t equal to 0 through the conditions y of x0 is fx and dou y by dou t at x0 is g of x. That is, here x lies between 0 to L. These two conditions are y of x0 is f of x and dou y by dou t at x0 is g of x, where f of x and g of x are functions such that f of 0, f of L is 0 and g of 0, g of L is also 0. These f of x and g of x may both be non-zero. Thus, to study the subsequent motion of any point of the string, we have to solve the following. Now, the solution of equation 1 subjected to the conditions 2 to 5. So, consider the equation dou square y by dou t square is 1 by c square into dou square y by dou t square. Let it be equation 1. So here the one-dimensional wave equation is dou square y by dou x square is 1 by c square into dou square y by dou t square. Now we will solve this equation by using method of separation of variables. So that first we have to define the solution for this equation. The solution can be defined as y of xt is x of x into t of t. Let me the solution for equation 1. Now computing partial derivatives dou y by dou x, that is t kept as a silent, x derivative is x dash. Dou y by dou t, that is differentiating partially with respect to t and keeping x as silent, that is x keep it as here silent and t derivative is t dash. Again differentiating with respect to x and again differentiating with respect to t, we will get dou square y by dou x square and dou square y by dou t square. Substituting these values in equation 1, we will get dou square y by dou x square is 1 by c square into dou square y by dou t square. Dou square y by dou x square value is x double dash t. 1 by c square into dou square y by dou t square value is x into t double dash. Now on separating variables, and the equation is equated to a constant, that is say it as lambda. So here lambda is constant. Now we will have three possible cases here arises. Those cases are lambda positive, lambda greater than 0, lambda equal to 0, and lambda may be negative, that is lambda less than 0. Now case 1, lambda positive. Since lambda is positive, say it as some p square, that is lambda equal to p square, where p is positive, then we will have lambda is replaced with p square. Now equating first and last, we will get a solution, that is x is a1 e power p1 px plus b1 e power negative px. Now equating middle and last, we will have a second ordinary equation on solving t equal to c1 e power pct plus d1 e power minus pct. Hence the solution is, let it be equation 1. That means just we have to replace these values in y of xt is x of x into t of t. Now case 2, when lambda is 0, now taking right hand side as 0, that means we are substituting lambda value in 0. Now equating first and last and equating middle and last, we will get another solution, that is H2. So here H2 is y of xt is a2 plus b2x into c2 plus d2t, where a2, b2, c2, d2 are arbitrary constants. Similarly, case 3, when lambda is negative, that is lambda less than 0, let lambda equal to minus p square, where p is positive. Now, equating it to minus p square and equating first and last, we will get x double dash plus p square x equal to 0, which implies that the solution is a3 cos px plus b3 sin px. Similarly, t solution is c3 cos pct plus d3 sin pct. Thus, we will have solution 3. So, these solutions S1 and S2 are not appropriate solutions, because in two cases we will get the displacement y of xt as 0, which is a contradict. Now, using considering solution 3, it is appropriate solution because they are having cos and sine terms as periodic functions. Since wave function is a periodic, so it must be a required solution. Now putting x equal to 0, y of 0t is a into c cos pct plus d sin pct. Substituting the values, we will get a value as 0. Now, putting x equal to L, we will get y of Lt is b sin Pl into c cos Pct plus d sin Pct, but y of Lt value is 0, equating to 0, sin Pl is 0, which implies that Pl is n pi, because sin n pi value is 0. That makes p value is n pi by L, where n varies as positive integers, that is 1, 2, 3 and so on. Now putting in solution 3, we will have solution y of xn yn of xt. So it is the most general solution. Now we can form the most general solution by taking the summation, that is taking different values of n, we will have a most general solution. That is y of xt is summation of n equal to 1 to infinity cn cos n pi ct by L plus dn sin n pi ct by L into sin n pi x by L. But we will have two more conditions, that is y of x0 is f of x, where f of x is summation of cn into sin n pi x by L. So put t equal to 0 in equation 6. Now cn value is 2 by L into integral 0 to L f of x into sin n pi x by L dx. Now we will have another condition, that is dou y by dou t at t equal to 0 is g of x. Thus we will have dou y by dou t is obtained just by differentiating y with respect to. While differentiating partially with respect to t, keep x as constant. Sin n pi x by L, which is treated as a constant. Now the derivative of Cn constant cos n pi ct by L derivative is minus sin n pi ct by L into n pi c by L. For similarly, second term dn constant, sin n pi ct by L derivative is cos n pi ct by L into n pi c by L. So it is the value of dou y by dou t, but at time t equal to 0, we will have g of x value. Now equating these, clearly LL get cancelled, thus we will have dn value. So thus we will have the most general solution of the wave equation is y of xt is summation of Cn cos n pi ct by L plus dn sin n pi ct by L into sin n pi x by L, where Cn value is 2 by L integral 0 to L f of x sin n pi x by L dx, dn is 2 by n pi c integral 0 to L g of x sin n pi x by L dx. So these are derived from half range sine series. Now, if the initial displacement is 0, then we will have f of x is 0. In this case, Cn value is 0. If the initial velocity is 0 of the given string, then g of x is 0. In this case, dn value is 0. These 2 points are very, very important while solving the given problems. Don't forget, initial displacement 0, f of x 0, Cn value is 0. Initial velocity is 0, g of x value 0, the value of dn value is 0. Problem: a tightly stretched string with fixed endpoints x equal to 0 and x equal to L is initially in a position given by f of x. The initial velocity is here 0. F of x is 2k by L x, where x lies between 0 to L by 2. 2k by L into L minus x, where x lies between L by 2 to L. Obtain the displacement at any point x and time t. The problem can be given also like this. Since the initial velocity is 0, we will have g of x is 0. That means dn value is 0. Now we have to find out the value of u of xt, so that we have to solve the one-dimensional wave equation, that is dou square u upon dou x square is 1 by c square into dou square u by dou t square, where u of 0t is 0, u of lt is 0 for all t, and u of x0 is f of x when x lies between 0 to L, and dou u by dou t at t0 is g of x, but in the given problem initial velocity is 0. That means g of x value is 0. Let it be equation number 5. Now, the most general solution which satisfying the equation 1, we have u of xt is summation of n equal to 1 to infinity Cn cos n pi ct by L plus dn sin n pi ct by L into sin n pi x by L. Using condition 5, clearly we have dn equal to 0. Now just we have to find out the value of Cn, which is given by 2 by L into integral 0 to L f of x sin n pi x by L dx. Just substituting f of x value in between 0 to L, that is 0 to L can be splitted as 0 to L by 2 plus L by 2 to L. Since the given function is discontinuity function at the point L, just we have to split the integration, and solving the integration by using the arrows method and then replacing upper limit value and lower limit value, we will get the required solution as that is Cn value is 8k by n square pi square into sin n pi by 2. Substituting in above equation, we will get the required value of u, that is u of xt is summation of n equal to 1 to infinity 8k by n square pi square into sin n pi by 2 into cos of n pi ct by L into sin of n pi x by L. It is the required solution for the given wave equation under the given conditions. Another problem: A tightly stretched string with a fixed endpoint x is 0 and x is L is initially at rest in equilibrium position. If it is said to vibrate by giving each of its velocity lambda x into L minus x, find the displacement of the string at any distance x from the one end of the string at any time t. So here we have to calculate the displacement x of the string at any distance small x from at any time t. So the displacement y of xt is satisfying the wave equation, that is dou square y by dou x square is 1 by c square into dou square y by dou t square, and satisfying these end conditions and boundary conditions. So y of 0t is 0, y of lt is 0, y of x0 is 0, and the initial velocity is given as lambda x into L minus x, that is g of x value. Since here f of x is 0, we have Cn value is 0. So now and we have to compute here only Dn value. Now it is the most general solution of the equation 1 subjected to these conditions from 2 to 5. So the most general solution is y of xt is summation of n equal to 1 to infinity Cn cos n pi ct by L plus Dn sin n pi ct by L into sin n pi x by L. Now f of x is 0, we have Cn value is 0. So just we have to compute here Dn value, which is obtained by using the formula 2 by n pi c integral 0 to L g of x into sin n pi x by L into dx. Just replacing the given function g of x, and then the integration is operated by using arrows method. That is, in isolate, the first coming function is x into L minus x, taking whose successive derivatives up to 0, and sin n pi x by L integrations up to 0. Now taking arrows like this, sin is plus minus alternatively. Now taking these products, we will get dn value as 0 when n is even. As n is odd numbers, then dn value is 8 lambda L cube by n power 4 pi power 4 c. Now substituting the value of dn in the above required displacement, that is y of xt is 8 lambda L cube by n power 4 pi power 4 constant. Just take it out from the summation, and summation is applied only for n term, that is 1 by n power 4 and sin of n pi c by L into sin n pi x by L, 1 by n power 4 sin of n pi ct by L into sin n pi x by L. Here summation n runs from odd integers, that is n varies from 1, 3, 5 and so on. For n even numbers, the value of dn is 0. So it is the required most general solution of the given wave equation under the boundary or initial conditions. Thank you.